Good day and welcome to Lab Talk, a series of expert tips to help you get the most out of our products in your lab. So today we have a great topic. It is a critical component of many different protocols and procedures in the lab. That is ultra-pure water. And today we're going to talk about the myths and the truths and debunk some of the myths, provide some of the truths for ultra-pure water in your labs. Without further ado, I'll introduce our speaker, Steve Karnak. He's one of our experts here on water purification, and he's going to have a great presentation here for you and a little demonstration to show how we can really optimize our use of ultra-pure water in the lab. Welcome, Steve.
Thanks, Angela, and hello, everyone. Let's get started. There are several myths about the measurement of pure water. Ultra-pure water is really not a natural state. Therefore, verifying its quality outside the water system requires some important considerations to understand. Today, we're going to explore and bust two myths of pure water measurement and actually measure conductivity and pH of ultra-pure water. So the first myth is ultra-pure water conductivity after dispensing should match the water system display. And myth number two is the pH of dispensed ultra-pure water should be 7.0. Let's dive in with our first myth. Again, the myth is ultra-pure water conductivity after dispensing should match the water system display. For instance, ultra-pure water usually measures 18.2 mega ohms per centimeter. So the ultra-pure water that I take from the system should read, when I measure it, 18.2 mega ohms also, right? Well, there's really more than that going on than we realize. The truth is that ultra-pure water immediately starts to pick up carbon dioxide and the conductivity starts to rise right when dispensing. So dispensed ultra-pure water will read a resistivity lower than 18.2 and a conductivity higher than 0.055 microsiemens. So conductivity and resistivity are inversely related. If we take the inverse of conductivity, 1 over conductivity, we get resistivity. On the screen, we usually read resistivity, but we're going to measure conductivity today in the lab. So therefore, as conductivity increases, conductivity decreases. A high resistivity of 18.2 mega ohms is the very same as a very low conductivity of 0.055 microsiemens. Okay, now that we've sorted that out, let's look at what affects the conductivity and resistivity of dispensed ultra-pure water. What's going on with our readings? Why are we seeing the effect of carbon dioxide? What we are seeing is the effect of carbon dioxide in dissolving in the ultra-pure water. This happens very quickly, and when it does, the conductivity will rise to about 1 microsiemen per centimeter, and the resistivity will fall to about 1 mega ohm. We'll show that in the lab here shortly. So at typical ambient pressure, 1 atmosphere, and 25 degrees C, there's about 400 ppm or 400 milligrams per liter of CO2 in the ambient air, which dissolves into the water very easily and creates bicarbonate ions that raise the conductivity and reduce the resistivity. For outdoor air, that's about 300 to 500 ppm is typical. When ultra-pure water is in contact with CO2 at this level, the expected conductivity rises. Crowded rooms can reach up to 1,000 to 3,000 ppm of CO2. In that case, conductivity can rise to almost 2 microsiemens, conductivity can rise to almost 2 microsiemens per centimeter. What causes these varying CO2 levels? Again, crowded rooms, the season of the year, plant respiration, human respiration, lots of different factors can change the CO2 levels. So again, the CO2 levels in the air, that's going to change the conductivity reading of your ultra-pure water. Now let's take a quick look how temperature affects ultra-pure water and the conductivity. The effective temperature on ultra-pure water is nonlinear. So the higher the temperature, the higher conductivity. So at 25 degrees C, we expect ultra-pure water to have a conductivity of 0.055. However, at a higher temperature, that conductivity will go to 0.071, and at a lower temperature, that'll actually drop down to 0.042. This means when we measure the conductivity of our ultra-pure water, we need to be aware of temperature. We will want to record the temperature and consider using temperature compensation when doing the measurements and adjusting that reading to 25C, depending on the criterion we are comparing to. If we do choose to use temperature compensation, we'll choose a nonlinear temp comp correction that's suitable for pure water. And now our second myth. The pH of dispensed ultra-pure water should be 7.0. Everyone knows the pH scale goes from 0 to 14. So after generating ultra-pure water, the pH should be exactly 7.0, right? And it's easy to measure. But again, there's more that's going on that we might realize. The truth is that ultra-pure water the pH of that can quickly decrease after it's been generated. Fresh ultra-pure water will read anywhere between pH 5 and 7. The pH will quickly drop. So that makes pH measurement of ultrapure water to be very challenging. These readings are very unstable and may be inaccurate also because of the low ionic strength of ultrapure water. Because if we think about it, ultrapure water has pretty much no ions in it. So what's going on with our pH readings? Again, we are seeing the effect of carbon dioxide dissolving into the water. We talked earlier about bicarbonate ions affecting and hydrogen ions affecting the conductivity, so it also happens with pH. So it happens very quickly. When the CO2 in the air is in contact with the water, it dissolves and forming the bicarbonate ions forms carbonic acid, which disassociates to those bicarbonate ions. It is the ions that cause the expected pH decrease, which we see in the ultrapure water as it's been dispensed. So should you worry about if a pH is 7 or not? It not equal to 7? Probably not. As we have seen, a pH between 5 and 7 can be attributed to just innocuous exposure of CO2 in the air. In addition, pH is not really considered a useful indicator of ultrapure water quality because of the expected CO2 absorption and the analytical challenges testing that ultrapure water. With this pH variation from 7, is that going to affect any solutions that I prepare with the water? In most cases, we don't expect to be a significant effect. CO2 will be present in any solution that we prepare in an air atmosphere. In general, it may be more useful to monitor and control the pH of the prepared solution than the pH of the ultrapure water used to make the solution. So do I need to adjust the pH of the ultrapure water before I use it? Again, in most cases, we don't expect there's any need to adjust the pH. While the pH may be noticeably different than 7, the acidity of the ultrapure water is negligible. It's not a highly buffered sample. So experts and standard organizations such as ASTM and USP agree that pH is not a useful indicator of ultrapure water. The pH of the ultrapure water changes to CO2 absorption and is an unbuffered liquid. A minute amount of CO2 absorbed in that ppm level will cause a deceptively large pH change. Additionally, the pH is challenging to read because of that low ionic strength, and the ultrapure water at pH about 5.7 is not significantly acidic. Now that we have discussed a couple of these methods and results, let's go over to the instruments and see if we can reproduce those results. So today we are going to dispense water from our thermoscientific Bornstedt GenPure Pro water purification system. We'll take ultrapure water out of the system, and then we'll move over to our thermoscientific Orion VersaStar Pro multimeter, and we'll measure the pH of the water and also the conductivity of the water. So let's take an aliquot. First, we'll measure conductivity. Again, ultrapure water at 18.2 megaohms is 0.055 microsiemens per centimeter. Just that little bit of time from taking the aliquot out of the system and bringing it over and measuring on the system shows a conductivity of almost 1.5 microsiemens, right? So, which would correspond to a little bit less than 1 megaohm. Next, let's measure the pH of that sample. So we'll take another aliquot. We'll rinse off our pH probe. And measure the pH. It started at 7, but it's quickly dropping just that fast with the CO2 absorption into the ultra-pure water. Remember, ultra-pure water has little to nothing in it, right? And water does not like being in that idyllic state, right? So it's going to try to grab as many things as possible and lower the pH. So we're stabilizing out just in that 30 seconds, already down at pH 6.7, which I mentioned earlier isn't really a problem. All right, so we did both myths, right? Myth 1 was the conductivity, myth 2 was the pH. So now if we look at summary, and we busted those myths, right? We busted those myths about ultra-pure water measurements of conductivity and pH. So myth 1, again, was ultra-pure water should match what's coming out of the system. And the truth is that picking up the CO2 from the air will change the conductivity. But one thing I want to make important is water is still considered ultra-pure because the CO2 can be accounted for. And then myth 2, the pH of the ultra-pure water should be 7. Again, the pH is going to quickly decrease after the ultra-pure water is dispensed because pH really isn't a good measurement of ultra-pure water. That ultra-pure water has a low buffer capacity and is also is picking up that CO2. So again, it's much more useful to monitor and control the pH of the prepared solutions than it is of the pH of the ultra-pure water when making that solution.
I just want to thank you again today for these helpful tips. As you mentioned, water is so critical to all lab processes, right? So we want to make sure that we're certainly keeping an eye on how we use our water and what type we use and when. If you have any questions, we do have a great support team. We have a full specialist team that covers North America, and you can reach us through going to thermofisher.com/ oh gosh, Steve, what's our...
Water purification?
Thank you. thermofisher.com/water purification.
Water
Sorry about
purification.
that. You can find us there. You can click on the contact us form. We will get you in touch with a person to help you locally as soon as possible, or you can ping us at learn, LERN, at thermofisher.com. Steve, I want to thank you for this great presentation. This will be one of our last presentations. We have one more next week on QC for microbiology. So if you're in the world of microbiology, please join us next week. We'd love to have you here. And that will complete our sessions for Lab Talk in 2023. So please join us next week on Thursday, same time. If you have any questions, again, thermofisher.com/water purification. Thanks, Steve. Have a great day, everyone.
Thanks, Angela.